Welcome to The Explainer. Today, we're going to completely demystify the beast that is the 100 kilowatt Type 14F HF broadcast transmitter. We are talking about a piece of equipment that produces an absolutely immense amount of amplitude-modulated power. I mean, it's enough raw energy to push a broadcast signal clear across oceans, typically operating right between 3.2 and 22 megahertz. But hey, rather than just dryly reading off spec sheets, we're going to break this giant machine down into bite-sized, understandable pieces. We'll explore its physical anatomy, see exactly how its electrical components talk to each other, go over the rigorous maintenance it demands, and figure out how to troubleshoot the whole shebang when things inevitably go wrong. Here is our roadmap for today. We'll cover the anatomy of the transmitter, functional block interrelationships, preventative maintenance tasks, common failure modes, restoration and troubleshooting, and finally, finding the schematics. Let's jump in.
Section 1. Anatomy of the transmitter.
Okay, let's dive into this. Imagine you're standing right in front of the 418F. You're facing a beautifully integrated master system. Over there, Unit 3 acts as your massive RF power amplifier. That's really the heart of the transmitter's output. Then you've got Unit 9, the modulator controller, which is busy processing all your external commands, and Unit 1 is handling the control and low-voltage distribution. Now, this front facade gives you access to all the good stuff, the control panel, the remote computer interface, and your critical tuning readouts. But to really grasp the sheer scale of this equipment, we've got to look behind it. Looking from the top down, you finally see the heavy lifters hiding in the back enclosures. The 4A1 and 4A2 high-voltage power supplies are back there executing the really serious power transformations, stepping down the high-voltage mains to actually feed the system. And right behind the modulator sits Unit 5, the cooling system, which is absolutely crucial. Notice Unit 7 too, the balun. That provides an impedance match between your final RF amplifier and the balanced transmission line. So yeah, the real muscle of this operation is housed right back here.
Section 2. Functional block interrelationships.
So, following the electrical journey through this thing is kind of like tracing a major city's power grid. You've got three-phase AC power rushing in through these heavy-duty high-voltage circuit breakers. Meanwhile, a 600-ohm balanced audio input is feeding right into the modulator controller. That audio signal, once combined with the power, hits the solid-state modulator. From there, the newly modulated signal travels to the RF circuits, where the actual carrier generation and amplification takes place, before passing through a harmonic filter and finally shooting out to the antenna or your dummy load. It's literally a perfectly synchronized dance of audio, raw power, and high-frequency radio waves.
Honestly, I always find it helpful to think of the transmitter as a living, breathing organism. Think about it. The RF power amplifier is the muscle. It takes the energy and shoves it out to the antenna with just incredible force. The control system and modulator controller, well, those are your brain and nervous system, right? They're constantly sending status signals, monitoring your power levels, and processing faults in literal milliseconds. And the cooling system is the circulatory system. Without a constant flow of coolant and forced air, the massive heat generated by the tubes and power supplies would straight up destroy the muscle in minutes. If one vital organ fails, the whole body goes down.
Section 3. Preventive maintenance tasks.
Keeping a system this complex running smoothly requires some serious, structured discipline. On a daily and weekly basis, you're doing quick health checks, things like verifying the VSWR, or voltage standing wave ratio, at sign-on and sign-off, just to make sure the antenna is taking the power efficiently. You're checking gas pressures on the transmission lines and doing a general physical walk-around. Now contrast that with the semi-annual stuff. This is your deep, surgical maintenance. You're in there replacing PA cabinet inlet filters, because trust me, dust accumulation will absolutely kill your cooling efficiency. You're opening up switch housings to look for any signs of arcing, and you're lubricating the motor drive mechanisms. It really is the difference between just checking your pulse and getting a full, extensive medical workup.
But despite all our best efforts, our careful routines, and our daily checks, the reality of broadcast engineering is that we are dealing with massive voltages and some pretty extreme environments. So, we've got to ask the big question: what actually happens when things go wrong?
Section 4. Common failure modes.
When failures happen, they generally fall into two camps. First up, internal mechanical failures. We're talking about something as maddeningly simple as a door interlock vibrating loose. That will instantly trip your safety circuits and knock the transmitter right off the air, costing you precious broadcast time. Or maybe loose hardware in the RF circuit starts causing parasitic oscillations, arcing and burning up contacts. Not good. Then, on the other side, you have external environmental attacks. Picture ice forming on guide towers and bridging your insulators, creating these massive leakage paths. You might even see corona discharge, which is literally glowing plasma, jumping off an antenna that's missing an end cap, making your VSW spike all over the place. It's a constant, ongoing battle against both internal vibration and external weather.
Section 5. Restoration and Troubleshooting.
Okay, so how do we fix it? The manual lays out a really systematic fault isolation procedure, and I want you to pay close attention to Step 1, symptom recognition. Honestly, this is always the most crucial step. Equipment troubles aren't always a direct result of a blown component. Sometimes it's just a condition of less than peak performance that doesn't immediately scream danger. Once you actually recognize the true symptom, then you move to Step 2, taking methodical measurements from the front panel meters. Only after that do you move to Step 3 to isolate the faulty circuit, and finally Step 4, replacing the faulty assembly. Never ever jump straight to swapping out parts without recognizing the true symptom first.
Now here's a feature of this system that is just an absolute game changer. Sometimes the transmitter can actually heal itself. Seriously. The 418F is equipped with automatic recycling circuits. Let's say the antenna takes a direct lightning strike, or maybe there's a temporary flash arc inside one of the vacuum tubes. These circuits will instantly detect that massive overload, shut the system down to protect itself, and then automatically re-energize the transmitter. It recovers from these transient temporary overloads all on its own to minimize your lost airtime, often getting you back to broadcasting in just a matter of seconds.
Section 6. Finding the schematics. But when you're really deep in the weeds trying to trace a complicated fault, the basic status lamps and front panel meters just aren't going to cut it. You need your ultimate treasure map. And for the 418F, that is Section 7 of your technical manual. Beyond just holding the drawings, this section is incredibly practical. Imagine staring at a complex circuit completely stumped as to why an interlock is open. Well, these diagrams give you exact signal name locators and backplane cross-references. They let you trace a specific signal path, drop a probe on an exact test point, and know precisely what voltage or logic state you should be seeing. It is quite literally the roadmap for the transmitter's entire nervous system.
So we've explored the physical anatomy, the electrical interrelationships, those critical maintenance schedules, and the systematic troubleshooting steps of the 418F. So I want to leave you with this. When a sudden failure strikes your station, will you be reacting blindly, just panicking at the alarm bells? Or will you be able to visualize the block diagram, clearly understand the symptoms, and know exactly which organ of this massive 100-kilowatt living system to check first? Thank you so much for joining me on this explainer, and be sure to keep that spatial and functional mastery sharp.